Welcome to all. Myself, Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today, I am going to discuss about Semiconductors Optoelectronics or Optoelectronics properties of semiconductor. So, let's start the topic. So, first, what is the optoelectronics? So, optoelectronics is the study and application of electronics devices that interact with light. Means, when light will interact with any kind of material and this interaction will be fruitful for any device application, then that type of device applications comes under optoelectronics part. Okay. The another definition is science and technology of electronic devices which involves interaction. Interaction means what? Emission and absorption with lights. Okay. So these are two adaptable definition of optoelectronics. Basically, optoelectronic is what? Interaction of light with matter, and that interaction, if work as a device application by utilizing the property of light and by utilizing the property of this interacting materials, then this thing will becomes under optoelectronics. So from figure itself obvious. See, this circle represents your core optics things, and this red circle will represent the electronics parts. So the interactions thing, optics plus electronics, which comes under optoelectronics. So basically, optoelectronics comprises with two things, optics and electronics. So before the study of optoelectronics, we should have some basic idea about electronics and optics. So here, before the going ahead in field of optoelectronics, we should know about some basic properties of semiconductors and some basic behavior of lights and its laws. What the laws followed by lights. Okay. So I will start with some overview or some introduction of first semiconductors, then some light behavior. So first I will start with introduction of semiconductors. But before that, I will give some example of optoelectronic devices. So here some examples of optoelectronic devices is given. So the first one is telecommunication laser, and the figure of this telecommunication laser is shown here. And this is where it is utilized. So this telecommunication laser will utilized in fiber optic communications, means in communication field. The second example is light emitting diode. So where this light emitting diode will be useful? It will be useful in advertising panel, mobile phones, and this is the figure of your light emitting diode. The next example of optoelectronic devices is blue laser. This is the figure of your blue laser, and that blue laser will be applicable in storage devices, medical diagnostics. Okay. Another optical fiber. So already it is well known thing, and it will be useful in communications and medical applications. The other optoelectronic devices is photodiodes. This is your photograph of your photodiodes, and it will be useful in camera, medical and safety devices. The other for optoelectronic devices is solar cell, and it is well obvious thing nowadays. The solar cell is very important in the field of renewable energy resources. So these are the some few examples of optoelectronic devices. Means what are these? Telecommunication lasers, light emitting diode, blue laser, optical fiber, photodiodes, and solar cell. So if anyone know about all these devices, are having some sort of knowledge, they definitely know all the devices made with semiconducting materials. Semiconducting material. So before going ahead in optoelectronic devices field, you must know about basic properties of semiconductor, how it will work, what is its characteristics, okay, how it will be made for device application. So for that reason, I am going to give here onwards some introduction about semiconducting materials. So semiconducting material is one whose electrical conductivity lie in between those of insulators and good conductors. Okay, means if you talk about in term of conductivity, semiconducting material is conductivity lies in between metals, or means perfect good conductors. Good conductors and insulator. So semiconducting materials conductivity is less than perfectly conducting material and greater than some sort of insulator. Okay, it is the definition on the basis of conductivity. If you want to give a definition on the basis of resistivity, you just reverse this symbol. But this is in terms of resistivity, rho. Okay, so in terms of resistivity, semiconducting materials having resistivity less than insulator but greater than conductors. Okay, so this is your classical definition that is given in many texts. But in terms of energy bands, so whenever the term bands is used, then definitely it is the quantum mechanical term, energy bands. Why? Because after the introduction of quantum mechanics, only we can able to define the origin of energy bands, so that in term of quantum mechanical definition or in term of energy band gap, the semiconducting materials energy band gap means Eg. This Eg represent the energy band gap. So energy band gap is greater than okay. So this relation is similar as a resistivity relation, means semiconducting energy band gap is less than insulator but greater than conductor. In case of conductor, we have seen many times there is no energy band gap or very small energy band gap. But in case of semiconducting material, these materials having some energy band gap around 1 electron volts, order of 1 electron volts, but that are too much less than in case of insulators. Okay, why? Because insulator have a energy band gap value more than 4 or 5 electron volts. It will be start up to 6 electron volts. So in term of so if you will go to define the semiconductors, so there are, you can define by 3 way. either on the basis of conductivity, sigma, or either in the basis of resistivity, or either in the basis of energy band gap. Okay. So here from pictorial diagram, I am trying to show what is the difference between conductor, semiconductor and insulator. So here you can see in the case of insulator, your band gap value is too high, but in the case of semiconductor, the band gap value exists but less than in the case of insulator. But in the case of conductor or metallic material, you can see the valence band and conduction band is overlapped to each other. Is overlapping means there is no energy band gap. So what happens in the case of conductor, the electron reside in valence band, and for conducting property, for conduction, it will move in conduction band. Okay. So here when valence band and conduction band overlap to each other, then a very small energy is enough to move the electron from valence band to conduction band, and it will make conduction, or it will take a part in conduction. But in the case of semiconductor, some more energy than valence band is required, so that electron will reach the valence band to conduction band, cross this barrier. Definitely the electron will require some energy. Why? Because some band gap is exist here. Okay. But in the case of insulator, this energy band gap is huge, so that it is next to impossible, so that electron will move from valence band to conduction band and make a conduction. So here I want to clear one thing. What is the energy band gap, EG? What is it? Is difference between here to here, here to here, or here to here. What is EG? So EG is basically, suppose if this is your valence band, this is your conduction band. So band means there are lot of energy value. Okay. And if you take collectively, it will form a band, energy levels. Okay. So a lot of energy levels here. Okay. Here also a lot of energy levels. So difference between lowermost energy level in conduction band, suppose this is E2, and uppermost energy level in valence band, suppose this is E1. So E2 minus E1 give the energy band gap value EG. Okay. So EG is what? What is the energy value here? Means top of the valence band. And what is the energy values here? Means bottom of conduction band. So suppose this is E2 and this is E1. Then E2 minus E1 give your band gap value EG. So this will imply for every materials, means in case of insulators, semiconductor and conductors. Okay. So these are two things. Here I define the semiconductors on the basis of conductivity or resistivity, or on the basis of energy band gap value. Here, the same thing is represented by pictorial diagram, and I clarified what is the EG. Okay. Now, material classification on the basis of order of resistivity and conductivity. So, resistivity rho, its unit is omega centimeter, okay, and conductivity sigma, its unit is Siemens per centimeter, and this rho and sigma generally inversely proportional to each other, okay, inversely proportional to each other. So insulator, in the case of insulator, it was observed that the insulators have a resistivity in between 10 to the power 8 to 10 to the power 18 omega centimeter. See how huge resistivity in the case of insulator, but in the case of semiconductor, its value lies between 10 to the power 8 to 10 to the power minus 3 omega centimeter, and in the case of conductor, the resistivity value lies in between 10 to the power minus 3 to 10 to the power minus 8. Means resistivity becomes too low in the case of conductor. So, same thing, if you want to define this classification in terms of conductivity, you have to inverse that order. So, conductivity lie in between 10 to the power minus 8 to 10 to the power minus 18. In the case of insulator, see how low conductivity. But in the case of semiconductor, it will be 10 to the power minus 8 to 10 to the power 3 Siemens per centimeter. But in the case of conductor, it will be around 10 to the power 3 to 10 to the power 8. Okay, so you have to keep all these order value in mind on the for the classification of insulator, semiconductor, and conductor. Okay. Here some examples of semiconductors, insulator, and conductors are given. So insulator, basically, if I want to give example of insulator, what type of material showing the insulating property? So the best example is glass, nickel oxide in pure form, diamond in pure form, and fused quartz. Okay, fused quartz. So here the one term is used, pure nickel oxide, pure diamond. So what its meaning? Means there is no lattice mismatch. Every atoms of nickel oxide, means nickel oxide comprises with nickel and oxygen, and these nickel and oxygen atoms will be situated at a particular lattice point. So each and every lattice point is well occupied by nickel and oxygen atoms, and there is no impurity. Means in the place of nickel, some another kind of element will be there. So that type of case will not possible for defining the pure insulators. Why? Because it will create some charge disbalance, and due to this balance of charges, some additional charges will appear, and it is possible they will make a part of conduction. They will play a role in conduction. So that's why this pure term is used. So glass, nickel oxide in its pure form, diamond in its pure form, and fused quartz. So it's some examples of insulators class of the materials. Now I am moving in semiconductors class. So primarily examples of semiconductors are germanium, silicon, gallium arsenide, gallium phosphide, and cadmium sulfide. Okay. And conductors class, so these are some conducting materials, means the examples are silver, copper, aluminium, platinum, bismuth. So these are some examples of these class of materials, means insulators, semiconductors and conductors. So okay, but one thing, why semiconducting material is, if semiconducting material, so the moderate conductivity or moderate resistivity. So in either side of semiconducting class material, one side insulator, one side conductors. So if you want a conductivity or conducting thing, so why you are not using pure conductors material? And if you want insulated thing, why you want insulator? Why you didn't use insulator materials? Why you always using semiconductors for device applications? Why it is so important? So that thing, answer of that questions is given here. We can change the conductivity of semiconductors, okay, and that thing, that property means we can alter, we can tune the conductivity of any material. That thing, tuning class, this is semiconductor is tuning class of conductivity, tuning class of material. So we can tune the conductivity of semiconductor, and that thing makes semiconductors too important for device applications. Okay, means we can change the conductivity. How we can change the conductivity? By illumination of light by appropriate wavelength. Okay, means if I want to change the conductivity of this class of material, so if we irradiate that semiconducting material by some appropriate light, appropriate wavelength light, so definitely it show the some varied conducting nature, and by changing the temperature or by adding some impurity element, means doping. So that tuning property of conductivity of semiconductors material make its too importance for device application. And how we would tune? By illumination of light by appropriate wavelength, by changing the temperature, and by doping. Okay. So here onwards, I am going to define the intrinsic and extrinsic semiconductors. Before this slide, I just defined the basic properties of semiconductor. Here onwards, I am going to some detailed explanation of semiconductors. So semiconductor are basically two types: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors means those type of material which show the insulating property at 0 Kelvin, but if we increase some temperature, it will show some conducting behavior. This class of materials example is germanium and silicon. So in its purest form, it is basically in its purest form, and at a 0 Kelvin, basically it is a insulator. But if we increase some sort of temperature, it will show some sort of conductivity. So best example of this class of materials means intrinsic semiconductor is germanium and silicon. The another class of semiconducting material is extrinsic semiconductor. Means extrinsic means we add some impurity atoms in natural materials, means in intrinsic semiconductor, and we derive some new class of material that is called extrinsic semiconductor. So the same thing is written here: for achieving the good conductivity in intrinsic semiconductor. Here, this is intrinsic semiconductor. Basically, it is an insulator at 0 Kelvin, but if we increase the temperature, it will show some sort of conductivity, not very good, moderate kind, even less than moderate kind. So for achieving the good conductivity in these material, intrinsic semiconductors material, we will add some sort of impurity, some kind of impurity atom, and that atom will mismatch or make a charged imbalance, and that charge imbalance will helpful for increasing the conductivity of this material. So for achieving the good conductivity in intrinsic semiconductor, doping of some impurity elements are required. Such type of material after doping are known as after doping. Means if we doped some sort of impurity atom in intrinsic semiconductor, then after doping, that intrinsic semiconductor itself called extrinsic semiconductor. Okay. So here by pictorial diagram, I am trying to show the intrinsic semiconductor. So here silicon atom lattice is given. So you can see every silica atom make a covalent bond with their adjacent silica atom, and if there is no charge imbalance, then there is no free electron available inside the lattice, means there is no conduction. Okay. So but due to temperature, means suppose if we increase the temperature of this pure silica lattice atom, so some covalent bond will be break inside the lattice, and this breaking of covalent bonds will be helpful for generation of electron hole pair, free charge carriers. Okay. Means if we break this covalent bond, then definitely some free electrons will be available. Okay. And that free electron will make a conduction. So why this free electron will be available? Due to bond breaking. Why this bond breaks? Due to temperature. When we increase the temperature, it is possible that some covalent bonds will be break, and by breaking of this covalent bond, some free charge carriers will be available. Okay. And when this free charge carriers will move throughout the lattice, the current will be flow. Okay. So this is the example of intrinsic semiconductor. Pictorially I represented here. So basically these class, intrinsic semiconductors materials class is what? Fourth group of periodic tables. Fourth group of periodic table, and not all fourth group element. 14 and 28 means germanium and silicon one. So best example of fourth group element, atomic number 14 and 28 means germanium and silicon. Okay. Now extrinsic semiconductor. Extrinsic semiconductor are semiconductors that are doped with specific impurities, and the impurity modify the electrical properties of the semiconductor and makes it more suitable for electronic devices such as diodes and transistors. So same thing is written here as I told earlier. When we want some more conductivity in intrinsic semiconductor, what we required? We required some doping, some impurity which will be added in intrinsic semiconductor, and that impurity will make a good property of intrinsic semiconductor in terms of conductivity. Okay. So the same thing is written here. Extrinsic semiconductor are semiconductor that are doped with specific impurity. The impurity modifies the electrical properties of the semiconductor and make it more suitable for electronic devices such as diode and transistor. So how we will dope? While doping in tetravalent atoms such as silicon or germanium, two types of dopant are generally used, and they are pentavalent and trivalent. Fourth group means tetravalent. This is chemistry term. Tri, tetra, penta. Okay. So tetra means 4. So tetravalent atoms means silicon and germanium. Silicon and germanium. Fourth group, tetravalent atom. While doping in tetravalent atoms such as silicon or germanium, two types of dopants are generally used, and they are pentavalent and trivalent. Pentavalent means fifth group element. Those elements having valency 5. So examples: arsenic, phosphorus, antimony. And trivalent atoms, atoms with valency 3 such as indium, aluminium, boron. So what is the methodology for deriving the extrinsic semiconductor? First, choose the intrinsic semiconductor, add some impurity on it. Intrinsic plus impurity. Impurity, if we add pentavalent, then it will become N-type extrinsic semiconductor. If we add trivalent, then it will become P-type of extrinsic semiconductor. N-type and P-type. Now, extrinsic semiconductor will be classified in two class, N-type extrinsic semiconductor and P-type extrinsic semiconductor. So, here silicon atom, lattice of silica atom is given, means fourth group element, intrinsic semiconductor. Now, if we add antimony, okay, antimony means, lead, PB, SB antimony, PB lead, fifth group element, PB, in silica atom lattice, then what will happen? One additional electron will be available. Why? Because this lead have a valency 5. So 4 electron will make a covalent bond with adjacent silica atom, and 1 electron will be rest there, and that will two free, means that will behave like a free electron. Why? Because it will require very less amount of energy, so that it will comes out from its octet. Okay, so it will be behave like a free electron, this excess electron. But in case of when you will add a third group element, means boron, in same lattice silica, what will happen? Efficiency of 1 electron. Why? Because boron have a valency 3. Okay, so 3 atom will make a covalent bonds with adjacent silica atom, but 1 electron is still required for making a covalent bond with another silica atom. So there will be deficiency of electron, and that deficiency will work as a hole, positive charge carrier. So P in terms also represent positive, not generally, but for remembering purpose, P means positive. And what is positive charge carrier? Hole. So you can remember as in P-type semiconductor, positive charge carriers is hole, and it will be basically a deficiency of 1 electron that will act as a positive charge carrier. Basically, it is not any exact particle, but it is a deficiency, and it will act as a particle. Here, and you can remember negative. So, negative, who will? Electron. So, here in N-type, majority charge carriers is electron, and in P-type, majority charge carriers is holes. Okay. So, these are some schematic representations of N-type and P-type extrinsic semiconductor. Now semiconductor, why? Already we defined semiconductor on the basis of energy band gap. So before going ahead in terms of optoelectronics properties of semiconductor, you have to know how this band gap or band structure will arise. How this band structure will arise in semiconductors. So I already told that this band, whenever the band words is used, means quantum mechanics already involved. Why? Because origin of band structure only explain on the basis of quantum mechanics. So this is the famous equation of quantum mechanics that is known as Schrodinger equation. You can go through your quantum mechanics book syllabus and you can find there. This is a famous Schrodinger equation. That is what? H cross minus H cross square upon 2m del square plus some sort of potential VR, and whole will be multiplied by wave function psi r, and its value is equal to E means energy and same wave function psi r. So this equation one we can also write as a H psi is equal to E psi. Okay, this H is what? Hamiltonian operator, operate on a wave function psi. Operator operate on wave function and give the value. Okay, always operator give the value. Okay, so H is a what? Operator. Which type of operator? Energy operator. So which value it will be given? Energy value. So this is eigenvalue of this operator H. Okay, so basically this is H, this is psi, this is energy value of this operator E psi. H psi is equal to E psi. So in the case of, generally it is found that any kind of material, the atom will be arranged in a periodic potential. So this is V is what? Periodic potential. So in a periodic potential, when constituent atom will be arranged in a periodic potential, then what type of wave function will be used? The question of answer of this question will be given by Blows, and they will provide the wave function of atoms which will be arranged in a periodic potential, and that wave function is known as a Bloch wave function, and it will be E I wave vector k dot r u and k r. Okay, that is the wave function psi. So you can put this wave function psi in equation 1 and you can solve that. Then you will find the energy value, and this energy value will be depend on the n and k, and this n and k must be an integer. Then this energy value will be discrete in nature, and then it will, that's why the energy bands are origin of energy bands. Energy bands will be appear. Okay, before the quantum mechanics, here the what is discreteness means energy have value in here, here or here, not here, not here. Okay, so some sort of discreteness, but before of quantum mechanics all energy value will be possible. Okay, so that is the beauty of quantum mechanics, and on the basis of assumptions of quantum mechanics we can explain the origin of band structures in semiconductors. So n and k, n is what? Integer value, k is wave vector. So the vector k can take a value belonging to the first billion zone. Actually, first billion zone, all kind of material, any material, lattice, or crystal structure follow some set of crystal structure, means simple, cubic, tetragonal, trigonal, and that crystal structure, if we go through your solid state physics courses, you will find out that there is a concept of billion zone. Okay, so the vector k can take a value belonging to the first billion zone, and n takes integer value. Okay, therefore all the possible energy level of solid can be labeled by the set of value nk. Okay, so why the billion zone is important? Why? Because all the property throughout, what will be the property of material, or what the property the material will show throughout the crystal structure, you can take all this property, or you can calculate all these property in a single billion zone. Whatever the property throughout the material, you can calculate same properties value in a single billion zone, and this billion zone is inverse of lattice constant A. Okay, 1 by A. So A is itself very small. So you can imagine what is the value of A. Suppose A is lattice vector, a value of lattice vector A. Suppose in case of simple cubic, ABC, so all ABC are equal. Okay, so what is the value billion zone? Value of billion zone, it will comprise in between minus pi by A to first billion zone. Okay, K. Okay, so all these thing, maybe here some hectic, it will become some hectic. So I will cover in any quantum mechanics course and solid state physics course. But here you can just remember this k value is very small, even smaller than lattice constant vector A. So how the beauty, by computation you can calculate this k value. And the most beautiful thing of this first billion zone, whatever the property of whole lattice, the same property will be reflected in this first billion zone. So if you want to calculate the band structure of whole lattice, suppose you consider the silica as a case study, and if you want to calculate the band structure of this whole silica lattice, you can calculate this band structure, same band structure of this considered silica lattice in a first billion zone, means inside that region. Okay, so if one plot E and K as a function of K for different integer value of N, one can obtain the band structure of solid. Okay, the first billion zone represent the FCC lattice or diamond or zinc blende lattice is shown below. Here the example of first billion zone. So here the center can be represented by X. This center of this face can be represented by X. Center of billion zone can be represented by gamma. So here I am giving the example of calculated band structure of some sort of semiconductor known as a germanium or silicon or gallium arsenide. So from here you can see silicon band structure. The top of the valence band is here, but bottom of the conduction band is here. Means no direct nature of band gap value. But in the case of germanium, top of valence band is here and bottom of conduction band is here. Means at the same K point, the top of valence band and bottom of conduction band exist. Okay, so here this is the direct nature of band gap. This is the indirect nature of band gap. here also in case of gallium arsenide, direct nature of band gap. Why? Because top of valence band and bottom of conduction band lie on a same K point. Okay. So here from this figure, the new thing you study here, direct nature of band gap. And first one is direct and second one is indirect nature of band. Okay. So when the top of valence band and bottom of conduction band lie on a same K point, then that type of band gap is known as a direct nature of band gap. And when it will be deviate from this definition, means top of valence band and bottom of conduction bands lie at a different K point. Here in case of silicon, top of valence band lie on a gamma, but bottom of conduction band lie on a X. So this is the example of indirect nature of band gap. So for optoelectronic application, the having the direct nature of band gap material, is important for device application in optoelectronic field. Okay. So for calculate, you can calculate the band structure or band gap value by nowadays some kind of software or some program is available known as a quantum espresso software. Another is WASP. Third one is CASTEP. Okay. So, or you can develop your own program. Okay. But these are the software where the program is inbuilt. Okay. So just you use the already developed program and you can calculate the band structure of any kind of material or any kind of semiconductor, and you can plot the band structure. Then you will get a plot like this. So from this figure, you can also know what is the band gap value, and also identify either it will be direct or indirect. Okay. And also you can calculate the conductivity. This slope of these bands is also very, very helpful for defining the conductivity of this material. Okay. So, how it will be helpful? You can calculate the effective mass value through this band, through considered band, and you can just say that what will be the conductivity through this band. Okay. So, these are some examples what we generally see in semiconducting optoelectronics device applications. Okay. And further, now you have a band structure. So photon will interact or absorbed by this valence band electrons, and it will reach up to conduction band. So what kind of energy should be inside the photon, or what kind of wavelength should be used so that the photon will be absorbed by a particular material? All the thing you can calculate by calculating the band structure. Okay. So in next video lecture, I will cover all these things: energy bands in solids, EK diagram, the band structure, the density of state in quantum well structure, occupation probability, and carrier concentration, and Fermi level, quasi-Fermi level, semiconductor material, semiconductor heterostructure, lattice matched layer, strained layer, epitaxial and quantum well structure, and band gap engineering. Thanks. I think for today it is enough. Thanks to all.
Like, share and subscribe. hit the bell icon for more updates.